Hello, right, here's a few more electrical circuit questions. We've got a starter with the following electrical quantities often used when analysing circuits. Draw a straight line from the quantity on the left to the units on the right. Right, potential difference, which we want to be thinking about conceptually most of the time anyway. We know this is our joules per coulomb, the energy per coulomb that's transferred between 2 points of a circuit. So potential difference, joules per coulomb. Resistance, well, from a V equals IR equation point of view, we're going to get volts per amp. That's just rearranging V equals IR, putting the units in. Less sort of conceptual way of thinking about resistance there. That's much more just straight units. Power, again, conceptually, rate of flow of energy, joules per second. So nice mix up there. Similarly with potential difference. Current, again, it's a conceptual one. It's a rate of flow of charge, coulombs per second. So at least three of those you want to be thinking about much more conceptually than just the units. Every time you're coming across potential difference, power or current, you want to be thinking in these terms. Joules per coulomb, coulombs per second, joules per second, that sort of thing. Right, part B, figure 3.1 shows a battery, EMF 6 volts, negligible internal resistance, connected in series with a thermistor and a 560 ohm resistor. Right, voltmeter across the resistor has infinite resistance. Well, I doubt that it does, but we can assume that it does for this question. Right, the reading on the voltmeter is 2.4 volts. Calculate the resistance RT of the thermistor. Okay, right, since I've got a bit of space here, I might do this in a couple of ways. I'm not a big fan of the potential divider equation. It just seems to be a little opaque, and I don't know, it's more trouble than it's worth. So let's go about this in a couple of ways then, as I say. So if we've got 2.4 volts across the 560 ohm resistor, then we know that we've got the remainder of the EMF across the thermistor. So we must have 3.6 volts across there. So we know these ratios of voltages and resistances are in proportion. They're in exactly the same ratio, whether it's voltage or resistance. That's how voltage is divided up, in proportion to the resistance. So if we've added 50% on in voltage, then we've added 50% on in resistance. So we can add on half of this, which is 280, and get 840 ohms. So that's one way of doing it. If you want to have maybe something a little bit more mathematical behind it all, then we can do the same and say we've got that 3.6 to 2.4. We got the 560 to some value here, which we're calling RT, aren't we? Well, if these ratios are the same, then we can turn them into fractions. This is the sort of stuff that we did back at the start of secondary school, before we even got the GCSE. So we turn them into fractions that are equal to each other, and then we just solve for this. So we're going to say that RT is equal to 560 multiplied by 3.6 over 2.4. This essentially is the potential divider equation. So we've got 1.5 there, so we're adding on 50% onto the 560. It's just the same old thing. I always go for this top approach because it's just so simple. And you don't have to bother with all of that, go into the formula booklet and pulling out whatever overcomplicated version of the potential divider equation they might have come up with. Anyway, that's that one. So we ended up with 840 ohms, didn't we, in the end? Calculate the current in the circuit. Right, the current is the voltage divided by the resistance. So our total voltage is 6. Our total resistance is 600 plus 800, which is 1400. So we got 3 over 700. We should probably just leave it like that. But if we were going to be figuring that one out, then we got 3/7 divided by 100. So 3/7 is 0.43. So we'd have 0.0043 amps if you're going to go to two significant figures, but you could just leave it as the 3 over 700. Right, okay, so that's that bit. Continues on. The variation of resistance with temperature for this thermistor is shown in the graph below. Use the graph to determine the temperature of the thermistor when its resistance is 800 ohms. Right, let's hope they've put this on a nice line. They have. They put it on that line, which is what, 1, 2, 3, 4 lines along. Now 10 going up to 50, so that must be 20 degrees C. Okay, we don't mind things like that. State and explain without calculation how the reading of the voltmeter in figure 3.1 will change as the temperature of the thermistor increases. Right, so this is our usual chain of reasoning that we want to do in all of this. So as the temperature of the thermistor increases, obviously you'll put this in sentences rather than my shorthand, that means that the resistance of the thermistor will drop. Then, so as the resistance of the thermistor drops, that means that the voltage across the thermistor will drop. As the voltage across the thermistor drops, the voltage across the resistor, call it R, will go up. Is that what we were going for? I've forgotten what the question is now. Oh yeah, so how will the reading on the voltmeter change? Yeah, so that is it, it's gone up. So we've got 3 steps to our reasoning here. You can see we're going along, and then we're using our finding of the first line as the starter of the second line. So we've got that sort of zigzag. That shows that, which then shows that, which then shows that. So a nice chain of reasoning that we've got going on here. All good. Circuit of figure 3.1 can be used as a temperature sensor. Temperature sensors are used in the kitchen to control the internal temperatures of ovens, typically 200 degrees C, and refrigerators 4 degrees C. So which device would this sensor be more suitable for? Right, so what we want is we can say that the sensor is best used when there is a large change in resistance for small changes in temperature. So in this case, I should go capital T rather than small t, suggests time, doesn't it? So yeah, we want a large change in resistance for a small change in temperature. So this happens near 4 degrees C, not at 200 degrees C. So therefore we want to use it in the fridge. So I mean, we can see this here. If we're down at 4 degrees C here, you get a little bit of a change. We've got a fairly big change here. Going from 0 to 20 degrees, you've got a large change here, 800 ohms up to whatever this is, 1100 or whatever. At 200 degrees, I mean, we can change from here to here and nothing's happened. I mean, the sensor doesn't even notice. So there we go. Right, so let's finish that first question. Onwards. Define resistivity of a metal wire. Right, resistivity we can define by writing out the formula and defining terms. So we can say R is, resistance, put of the wire at the end, just so we're linking it up to the metal wire that's in the question. So resistance of the wire, A is cross-sectional area of wire, L is length of wire. So just writing all those out. In the UK, National Grid is used to transmit electric power. Each pylon supports 24 cables. Each cable consists of 38 strands of aluminium. Actually, they quite often put steel in the center for the center strands to give a bit more strength. Aluminium's light, but it's not quite as robust as steel. But anyway, I'd imagine for ease of calculation, they've put all aluminium here. Resistance per kilometer of a cable is 0.052 ohms per kilometer. Explain what a resistance per kilometer of a single strand is that. Right, so if you think of what's going on with all of these strands in a cable, they're all really acting as parallel resistors. Each strand has got its own bit of resistance. But when we come into the cable, we've got 38 of these, all in parallel, really. So we're using our parallel resistors formula here. We can say that the total resistance for 1 kilometer is 0.052 ohms, and that's going to be 38 strands. So that's 38 lots of 1 over whatever the resistance of one strand is. So to the power of -1. This is our parallel resistors formula. 38 resistors that are all the same. You put them into the formula and we're getting this as our setup. So we just have to solve this for RS. So RS is going to be equal to 38 times 0.052. I mean, 0.052 is pretty close to 1/19, which is why we're going to get nearly 2 as an answer. But I'm going to put it into the calculator just to make sure. 1.976. So that's 2.0 ohms per kilometre to 2 significant figures. Excellent. Right, next bit, resistivity. They've given us that and they want us to work out the cross-sectional area. Right, okay. That's in ohm meters, so we want to get everything into meters. Our cross-sectional area is then, well, the resistivity, 2.6 times 10 to the -8, multiplied by a bit of length. Well, we know we've got 2 ohms per kilometre. So let's say we've got 1,000 meters then, because we can then set our resistance to be 2. And then we just stick all that in, and we've got 1.3 times 10 to the -5 meters squared. And that was a nice, easy one. C, calculate what? Oh, we got input voltage is this. So we got 400 kilovolts going into the cables. Yeah, the cable carries a current of 440 amps, right? And then calculate the input power, number of cables, the power loss, and then some kind of percentage at the end, right? Okay, so again, let's just be clear on these. And I've gone through this sort of many times when it comes to these power cables. But you've got cable in, cable out. This is what's coming out of our power station. This is going off to some transformers somewhere else. But yeah, we have to have cable out and cable in some way, or you've got to ground something somewhere else. But still, say we got cable out, cable in. The 400 kilovolts is the potential difference between these cables. So if our input voltage is the 400 kilovolts, we're just saying, well, we got 400 kilovolts here, but we got nothing on the other side. It's the difference between our live and our neutral. If we were thinking about 230 volts at home. So it's important not to use this in the wrong way, this 400 kilovolts. We're not using that for power loss when we get down to part 3 here. But we can use it for the input power to the cable, because our input power is going to be our current times our voltage. So that's 440 multiplied by 400,000. So 444s are 176. And then how many zeros have we got? 1, 2, 3, 4, 5, 6. So well, actually, if we leave it with 6, we've got 176 megawatts. So 180 megawatts to 2 significant figures. So that's our input power. So how many cables do we need for 200 megawatts? So, 2,000 megawatts, sorry. So 2,000 divided by 176. Well, 11's not going to be enough. Would 12 take us over? 12 would take us over. So we need to round up, because you can't have a fraction of a cable, can you? So we're going to need 12 cables to get us past the 2,000 megawatts. Power lost as heat per kilometre of cable. Right, and this is where I'm saying you don't want to be using this input voltage, because of course the power loss is to do with the potential difference along one cable, not between the input and output cables. So we've got 2 different voltages we're talking about here. The potential difference between the cables and the potential difference from one end of a cable to the other. So we can't use that 400 kilovolts, because that doesn't apply to the cable that's going out. So we have to do, if we're going to do power loss, we need to do an I²R. So this is per kilometre. So in 1 kilometre of cable, we've got this 0.052. I think that, yeah, that's our 1 kilometre. So we need to do 440 squared, that's our current, multiplied by 0.052. So that's definitely going to be a calculator jobby on that one. So that is giving 10 kilowatts, pretty much. It's a little bit over, but two significant figures. Once more, we've got 10 kilowatts. So what is the percentage of the input power that's available at a distance of 100 kilometers? So if we're losing that every kilometer, so lost in 100 kilometers is going to be equal to 10 kilowatts multiplied by 100. So that's going to be 1 megawatt. So we're losing 1 megawatt in 100 kilometers. And so percentage of the input power that's available at a distance of 100 kilometers. Right, okay, so we've lost 1 out of 176. So we've got 175 over 176 left after 100 kilometers, which is going to be over 99%, obviously. So that's 99.4%. Nice one. Is that the end of that question? Yes, it is. Right, I've got one question to go. Question is about the use of a thermistor fitted inside an oven. Right, okay, so we're still on thermistors, but no fridges this time. Temperature sensor and a potential divider circuit. Yes, so this is the circuit. We've got R2 in parallel to some electronic circuit that's switching the main supply to the heating element. Right, so as the temperature changes on R2, the potential difference across it is going to change, and that's flicking on and off the oven heater. As it cools down, it's going to turn on, and it heats up, it's going to turn off again. So this is sort of your thermostat for your oven. Right, variable resistor R1 and thermistor R2, the circuit symbols are incomplete. So put these on. So variable resistor R1. That means we've got the arrow going through it, and the thermistor for R2 is that like bent line thing. So that's just knowing your circuit symbols. Now we've got some calculations and graph work by the look of it. Required that the PD across the thermistor is 7 volts when at a temperature of 180 degrees C. Right, we've got this graph here. Use the graph to determine the resistance at 180. Right, 180, 1, 2, 3, 4, 5. Right, this is all wonky eyes time. Go up that line. Oh, it's hit a nice point. It's hit the thick line. All right, it's hit a 500 ohms. That's good. So 500 ohms. That was an easier one to read than usual. When the temperature is 180 degrees C, the PD across R2 is 7 volts. Calculate the current in R2. Right, okay, well, the current is equal to the voltage divided by the resistance. So 7 divided by 500. So, well, 1 over 500 is 0.002 multiplied by 7 is then going to give us 0.014 amps. All right, that's good. The electronic circuit draws a negligible current. Show that the resistance in the variable resistor must be about 350 ohms. Right, so this is just our proportionality stuff again. So we've got, what have we got? 500 ohms and 7 volts. So we've got 5 volts across the other one. So we're just putting these into proportion of each other. So we're dividing things out, in the way that we normally do. So we need to divide 500 by 7 and multiply by 5. So 500 divided by 7 multiplied by 5 is going to give us, oh, blimey, I could go through doing all this, but I'm just going to stick it into the calculator because it's just too much to mess around with. I think it's going to be 357 1/7, so 360 ohms. Sometimes you just can't be bothered to do the mental maths, particularly when it's got 7s in it. Although it probably wouldn't have been that bad, actually. I'm kind of tempting myself into doing it now. You're going to get 71 3/7 multiplied by 5, which is 355 plus 2 and then a 7th, so 357 1/7. Yeah, so actually it wasn't as bad as I thought it was going to be. Anyway, didn't really need to do that, but yeah. Last part then. So R2 is heated slowly. Show that the PD across R2 must fall to about 5 volts when the temperature of R2 reaches 200 degrees C. Right, so at 200 degrees C, we've got 1, 2, 3, 4, 5. So around about here, round about there. So that looks about 250 ohms we seem to have here. So if we've got 250 ohms, we're doing this again. It's the same old. So they haven't changed the other resistor. So we've got 360. I mean, they're saying all about now. Let's stick with a 350 because it's going to be easier, and they're giving us about. So we've now got 350 to 250 for dividing up our 12 volts. So you can see we've got here in total, we've got 7 50s there and 5 50s there. So we're dividing them up. That's going to be 7 to 5. So we're going to now have 5 volts across the R2. So yeah, we're just dividing up in proportion again. So you can just put a little sentence in your answer saying PD divided in proportion to resistance. Proportion to resistance. Now, I think there's one more little bit of this question to go. There is. So the thermostat R2 is fitted inside the oven. When the PD falls to 5 volts, it switches off. When it's at 7 volts, it switches on. Right, okay. We've now got R1 at 250 ohms. Calculate the temperatures. Right, so we're recalculating all these things. So we've got 5 volts, it switches off. We've got 7 volts, it switches on. Right, okay. And we've got 250 ohms. So we've got 250 ohms, which is the R1. And we've got some resistance for the other one. So this is our R for the thermistor. Actually, what they're calling it R2, aren't they? Let's call it R2. And so when it's off, we've got R2 is at 5 and that's at 7. So this is for off. So, and then for on, so that's off. For on, we're now going to have the other way around. We're going to have 250, we're going to have 5 there and 7 there for R2. So this one's going to be a lot easier to do because we can say here that R2 is going to be equal to 350 ohms. So that is when it is on at 350. This one is going to be a little bit more annoying. Our R2 is going to be equal to 250 divided by 7 multiplied by 5. So right, this time I'm just going to go to the calculator and not get suckered into it. Right, that's coming out about 178 ohms. So we're going to have to go back to the graph and find the temperatures associated with these. So for 350 ohms, where are we? 350 ohms. So we're going up to around about, where are we? About here. And then across is giving us that bit. So it's about 190 to 195, something like that. Seems to be. So that's, I don't know, let's say 190 to 195 degrees C. They'll probably give you a bit of leeway. And then we've got 178 ohms. So 178, oh good grief, I mean this is going to be somewhere around here. What's that? Around about 210 and a bit. I mean, it's not going up all that quickly on here, is it? So let's say, oh, actually, these are quite big gaps, aren't they, between these? So yeah, that's up nowhere near as much as 195. The last one, I was misreading the scale. So let's say 190 and 210. That's close enough for trying to deal with this. Yeah, this sort of thing. They give you quite a lot of leeway on reading off those graphs, particularly as we've got assumptions kicking around all over the place on this. And you know, approximations, you know, trying to read 178 ohms off of that thing is nigh on impossible anyway. So again, it's all potential divider stuff. So just get used to, I mean, you can use a potential divider equation, I suppose. It's not like it's a disaster if you're using that. I just don't like it personally. It just seems unnecessarily complicated to compared to just doing these ratios. It's so much quicker just doing this. And if you've got used to doing ratios, as hopefully you have done in your maths, then it's just really, really quick. You don't even have to do any proper working out. It's just stuff you can work out in your head. So anyway, they were 3 nice questions.